In this example, we have a disk with radius 12 meters and mass 500 kilograms. And we've got a kid who has mass 40 kilograms who's standing 5 meters from the axis. The disk with the kid attached to it, presumably the kid is standing in one spot on the disk, is spinning. I guess you could describe that as counterclockwise when viewed from above or clockwise when viewed from below, but rotating this way. Spinning at 10 rotations per minute initially, and then the kid walks from the 5 meter mark out to the edge of the disk. As that happens, as the kid walks, what would you expect to happen here?
So would the moment of inertia of the kid change?
Yeah, and specifically, would that be increasing or decreasing?
It would increase because the radius would become larger.
Yeah, moving some of the mass out to a larger radius is going to increase the moment of inertia. And we could say that's increasing the moment of inertia of the kid, which is true. But also, since the kid and the disk are rotating together, we can treat them as one unified object and say that the total moment of inertia of this system is increasing. And can we treat this as a closed system as far as torque is concerned? Is there any external torque or not?
No.
No external torque, right? Because presumably the only forces acting on this would be what sort of forces? Or where would the forces be located?
Would it just be like gravity?
Yeah, we've got gravity, and gravity is going to be pulling downwards, presumably at the center of mass. And the kid is going to, the location of the kid is going to bias the center of gravity a little bit out to the side, but I think we can treat it as located pretty close to the center, since most of the mass is the disk itself. So the center, the force of gravity is pretty close to the center, so that applies effectively no torque. Because torque, at least the magnitude of torque, is radius times force times sine theta. If the force of gravity is located really close to the pivot point, then that means R is very small, so we get almost no torque from gravity. And what other forces are acting on the object? Acting on the disk? Is the disk in the process of falling?
No.
Gravity is pulling it down. So what's holding it up?
Oh, the normal force?
Yeah, presumably we got a normal force from the axle itself. This is presumably mounted on some sort of solid axle. It's rotating around, gravity's pulling it down, but the axle is holding it up. So the axle is, again, located at the pivot point, the center of rotation. So that means it provides no torque. There's a strong normal force canceling out the force of gravity, but it's located at location 0. It's located at the pivot point, so it provides no torque at all. Any force acting on the pivot point itself provides no torque. So we can assume this system overall has no torque, or at least very little torque. So we would assume that the moment of inertia, or sorry, the total angular momentum does not change. So L total initial should equal L total final. We should assume no overall change there. And moment of inertia, or sorry, angular momentum can be written as what times what in general? How do we define angular momentum?
I times omega.
Right. So in total, we can say moment of inertia initial times angular velocity initial equals moment of inertia final times angular velocity final. And we could split that up into the I times omega for the disk and the I times omega for the kid. We could treat those as separate objects. But if we did that, we'd have moment of inertia initial for the disk times angular velocity initial for the disk, plus same for the kid. Equals final of all that. Final moment of inertia for the disk times angular velocity final for the disk And same final for the kid. However, if the kid is attached to the disk, if the kid is standing on the disk, what do we know about their angular velocities?
It should be equal.
Right. They're rotating together, so they have equal angular velocities. So we don't need to separately label angular velocity of the disk and angular velocity of the kid. They're rotating together, so they have the same initial angular velocity. And at the end, they're also rotating together, so they have the same final angular velocity. And if we've got the same multiplier in both of these terms, what can we do with those terms?
We could do I disk plus I kid in parentheses times omega initial.
Yeah, we can just factor that out. The total moment of inertia of the combined object, if you imagine the disk and the kid as one unified object, times that angular moment or angular velocity. And same thing for final. We can factor out omega final from both of them because it's the same omega final. So because they're rotating together, because the disk and the kid are rotating together, both before and after, we can factor out the omega from each side of the equation and just get the combined total moment of inertia. And this ties into the idea that if you've got a system of objects all rotating together as one object, you can just add their moments of inertia to get the total moment of inertia of that unified object. Any questions on that so far? So how do we calculate these moments of inertia? We know the initial angular velocity, that's the 10 rotations per minute, but we're trying to find let's say we want to find the final angular velocity. Actually, before we even do that, would you expect the angular velocity, would you expect this rotation to get faster or slower?
Should it be slower?
Should be slower. And how can we tell?
Because combined mass, I guess, would be greater. And then the moment of inertia would be greater.
Yeah, the mass isn't changing, but it's getting further away from the pivot point overall. That the kid is moving away from the pivot point, so that should generally increase moment of inertia. And if the moment of inertia overall has increased, then the angular velocity has to decrease because those changes have to balance each other out to a constant product. So we're going to get a slower angular velocity than before. So let's try this out. Let's see if we can actually calculate these. To begin with, we probably want to find all the relevant moments of inertia because we have the initial angular velocity. Initial angular velocity is just the 10 rotations per minute. At least that's the magnitude. And usually we write angular velocity in radians per second, but rotations per minute is fine as long as we're not going to be doing any sort of conversions. As long as you're just changing an angular velocity into another angular velocity, which is what we're going to be doing here, you can leave it in whatever units it's already in. If you're going to be messing around with how that angular velocity relates to a torque, you should put it in radians per second so you've got consistency with all the other units. But if you're just taking an angular velocity and you want your result to be another angular velocity, you can just leave it in whatever units it's already in. So we've got omega initial, we want to find omega final. That means we're going to need both moments of inertia. Let's start with the kid. How would you calculate the kid's moment of inertia?
We could just treat it like a point mass. So do mr squared.
Yeah, for the kid, we can just multiply mass times radius squared because the kid is effectively a point mass here, as you say. It's an object that is small compared to the other distances. All the mass of the kid is effectively at just that one location. So we've got mass times radius, that'll be the 5 meters that the kid is from the pivot point, squared. So 40 times 25 would be 1,000. At least before the kid moves. But after the kid moves, what's going to happen? What would be different about our calculations?
You would have to use 12 after he's moved outwards.
Right. After the kid moves, we'd be using 12 meters instead of 5 meters. So let's try our final as well. If we take 40 kilograms times 12 meters squared, that's 144 times 40, which is 400. Yeah, let me just be quick about this. So 5,760 kilogram meters squared is the final moment of inertia of the kid. But of course, the kid isn't the only object in the system. We also have to consider the moment of inertia of the disk. And how would we calculate moment of inertia of a disk like this, a solid disk?
Is that one of the values that they give in like the table?
Yeah, there should be a formula for that. So we can just look that up. If you've got a list of formulas like this, just a formula for moment of inertia for each of various different shapes, like a ring or a rod rotating around its endpoint or a rod rotating around its center, a disk, a solid sphere, a hollow sphere. In this case, a disk makes the most sense here. So that'll be 1/2 mr squared. So I'm going to write this as 1/2 times, let's say we're using capital M for the mass of the disk. And I'll call this capital R squared for the radius of the disk. So that's 1/2 times mass of the disk, 500 kilograms, times its total radius, 12 meters. So that'll be 144 times 1/2 is 72, times 500 is 3,600. $36,000. So that would be the moment of inertia of the disk. And does that change as the kid moves?
No.
That doesn't change because the kid moving changes R for the kid from 5 meters to 12 meters. But the kid moving doesn't change the properties of the disk itself. So we can treat the disk as staying the same, or at least keeping the same moment of inertia. And I think now that's enough information that we can fill in the equation we've got here. Moment of inertia initial for the disk and final for the disk are both 36,000. So initial and final momentum or moment of inertia for the disk, those are both 36,000. And then for the kid, initial was 1,000. And final was 5,760. And we also know the initial angular velocity. The initial angular velocity was 10 rotations per minute. Actually, I'm just going to leave that as omega initial for now. We can fill in the value later. But if we just add up these moments of inertia, we end up with a total of 36,000 plus 1,000. So that's 37,000 kilogram meters squared times omega initial. And then on the other side, 36,000 plus 5,760 would be 41,760. Times omega final. So that gives us an equation relating the initial angular velocity and the final angular velocity. Any questions on that so far? And we know the initial angular velocity. How would we solve for the final angular velocity?
divide the left side of the equation by 41760.
Yeah, we can just divide both sides by that final total angular momentum, or final total moment of inertia, I should say. Because that's really all this number is. This number, 41,760, is the final moment of inertia of the whole system. So what we're really dealing with here is the final angular velocity, because these cancel out, is the initial angular velocity times the ratio of initial total moment of inertia over final total moment of inertia. So that's our omega final. You could even write this as initial moment of inertia over final moment of inertia times omega initial. But we can actually fill in the numbers here. 37,000 divided by 41,760 is about 0.886. So that's the multiplier. This is that ratio of initial over final moment of inertia. And note that this is unitless. The kilogram meter squared and kilogram meter squared cancel out. So thus far, it doesn't really matter what units we use as long as we're consistent about it. This ends up being a unitless ratio. We end up with the final angular speed being about 88.6% of the initial angular speed. And if we fill in the value there, omega initial was 10 rotations per minute. 10 rotations per minute. So like I said, it doesn't really matter what units you're using for omega initial because you're just multiplying it by a scaling factor. You get 88.6% of 10, which is about 8.86 rotations per minute. So it has slowed down. The whole system has slowed down from 10 rotations per minute to a little bit less than 9 rotations per minute. And does the direction of rotation change?
No.
No, it shouldn't, right? I mean, first of all, conceptually, if the kid moves around, that's going to make the rotation faster or slower, but it's not going to change the direction of spin. It's not even going to change the axis of rotation. And we can even see that mathematically here, where the final angular velocity vector is the initial angular velocity vector times a positive scalar. And multiplying by a positive scalar does not change the direction, it only changes the magnitude. So the angular velocity vector is still going to be the same direction as it was before. And by the way, so far we've just been working with magnitude here, but how would you determine the direction of the angular velocity vector? If you wanted to know the direction angular velocity is pointing here. How could we assign a direction to omega?
I'm not too sure, but do we have to use the right hand rule to determine where it's rotating?
And before we even use a right hand rule, we can narrow it down to two possible directions, because in general, the direction of an angular velocity, or really any rotational quantity, is supposed to be along the axis of rotation. This disk is rotating around what sort of axis? What direction of axis? Is the axis of rotation left and right, forward and backward, up and down, north, south? What's the axis of rotation here? Yeah, this is an up and down axis of rotation. This whole object is rotating around a vertical axis. It's spinning around an axis that's straight up and down. You could even think of this as the physical axle. The pole that everything is rotating around is a vertical pole. So that means that the only possibilities for the angular velocity are straight up and straight down, because that's the axis, the vertical axis that this is rotating around. To choose one of those two, once you've narrowed it down to two possibilities, you use the right hand rule. This object is spinning like this. So curl the fingers of your right hand in the direction it's rotating. Is that right? Yeah. The side close to you is curling this way. So turn your fingers of your right hand this way. And now my thumb is pointing upwards. So this rotation, curl the fingers of your right hand in the direction of rotation, and your thumb's now pointing upwards. So that means the angular velocity vector is upwards here. And of course, that doesn't mean anything's moving upwards. It's just talking about the axis that this object is rotating around. That's the meaning of the angular velocity vector's direction, the axis of rotation. So we'd say the final angular velocity is 8.86 rotations per minute in the upwards direction. You could also interpret that as counterclockwise when viewed from above or clockwise when viewed from below. But it's more precise to specify in terms of a linear direction based on the right-hand rule. Any other questions on that one? Or any other questions on the rotational stuff in general?
I think I understand it a lot better now. Thank you for walking through the example.
Yeah, glad it could help. And let's try some stuff with the forces and Newton's law as well. Let's try an example with, let's say, a car turning a corner. Let's say you have a road. So this is a top-down view, like a map of a road. And you've got a car traveling along this road. And let's say this car is traveling at some velocity v. And let's say we want to figure out the speed limit on this road. We want to figure out how fast can the car go along this curve safely. Because if you're going on a straight road, if the road is completely straight, then as long as there's no other obstacles, no other cars, if you are literally if you know absolutely for certain that you're the only thing on a straight road, then you could in theory go as fast as you like and you'll just continue on a straight line. Of course, you don't want to actually do that in real life because there might be some obstacle you don't know about or something coming onto the road that you need to stop in time. But if you've got a curved path, then there's a much more practical lower speed limit, because if you're going too fast on a curve, what's going to happen? What would happen if you're going really fast and you try to turn? Yeah, you're going to go off the road. You're going to skid off the road instead of turning properly. Because if there's no forces on an object, what sort of path is it going to travel in? If there's no forces at all, yeah, it should travel on a straight line. Continue on an original path, and specifically I would say the original straight line path. It's going to continue in the direction of its velocity vector. Its velocity vector, let's say, is this direction, so it's going to continue on that straight line if there's no forces acting on it. So with no forces at all, or if there are forces but they add up to 0, the object's going to continue in a straight line. If you want an object to go on a curved path, there has to be a force acting on it, and specifically a force pointing in what sort of direction? What direction does the total force have to be in order to make the object go on a curved path? Yeah, it's got to be inwards. There's got to be a net force in the inwards direction in order to make this go on a curved path. Because without that force, it would go in a straight line. With that force, it's going to curve in the direction of the force. So it is able to go on this curved path. And specifically to get more detail about that, any small curved path you can treat as a portion of a circle. Even if the curve is not an entire circle, if it's not a complete circle track, you can treat this portion of the track as a portion of a circle. And that net force then has to be straight towards the center of the circle. And what do we call the direction towards the center? Yeah, this is centripetal. Centripetal is literally just Latin for towards the center. Centrifugal means away from the center. Centripetal means towards the center. The centripetal force. And I want to emphasize centripetal force isn't a type of force like force of gravity or normal force or friction force or something like that. Centripetal is literally just a direction. When we talk about a centripetal force, we just mean a force toward any force towards the center of the circular path. And that could be provided by any force you want, depending on the situation. In this case, what is providing the inwards force here? What force on the car is providing an inwards force, a force towards the center of the circle? Yeah, the friction of the tires, the friction between the tires and the ground. And if it's difficult to see why this is friction, I find it's often useful to imagine what would happen if there was no friction or if there wasn't enough friction. Like if this was a very smooth, icy, slick road, what's going to happen to the car when it tries to turn? Yeah, it's going to slide around. Specifically, you turn the wheels, but nothing happens. It just keeps sliding in a straight line, or mostly a straight line. So if lack of friction means the car is going to skid off in a straight line, presence of friction is what allows it to turn in a curved path. So the presence of friction is what's making it turn here. Friction, the side-to-side friction between the tires and the road. Not the forward and backward friction. That's what allows it to accelerate forward by pushing the gas or slow down by hitting the brakes. But the sideways friction is what's allowing it to turn. So this net force here, the inwards force, was presumably caused by the friction between the tires and the road. And if we draw a free body diagram here, let's say we take a look at a back view of the car. We've got a back view of the car. So we've got the tires, the car itself. What forces would you say are acting on the car as it moves? Yeah, we definitely have a force of gravity. And how would you determine how strong that is? What's the usual calculation for how strong the force of gravity is? Yeah, the mass of the car times, or in general, let's say G. So M times G. And we don't have to worry about the negative value on G in this case. I mean, typically we would treat gravity as negative 9.8 meters per second squared, or round it off to negative 10. But in this case, we're treating G as just an absolute value for the magnitude of Fg. The downward sign is the downwards is already taken care of by the direction of the vector. So force of gravity is magnitude M times G. And then a normal force, and this is going to be distributed over all the tires, but it might be useful here to treat the car as just one object, or one single point. Because we don't really care so much about torque here. We can treat the car as just one object. So we've got force of gravity pulling downwards. We've got a normal force pushing upwards. And what do we know about how strong that one is? Or actually, let's not fill in the strength of that one yet. Are there any other forces acting on the car? We know there's a force of gravity. Presumably there's a normal force from the road because it's not sinking through the road. And yeah, we've got to have a force of friction. And which direction would you expect that to be here? If this is a back view. We need the total force to be in which direction here? We need the total force, yeah, we need the total force to be to the right. Because this total force, the net force, is what's causing it to curve towards the, curve along the direction of the track. And the only side-to-side force that's available here is friction. Gravity is not going to help because it's pulling straight down, not towards the center. Normal force is also pushing straight up, not towards the center, so that doesn't help. The only force here that's really going to be relevant in terms of contributing to the net centripetal force is the force of friction. And this is the side-to-side grip strength of the tires. That the car is trying to slide forward but the grip strength between the tires and the road is pulling it to the right. So we've got a force of friction, and that force of friction is what's providing the centripetal force here. In fact, the force of friction is the net force, which is F centripetal. Because what do we know about the normal force and the gravitational force here? Yeah, in this case, they're going to cancel out. Because the road, we're assuming the road is horizontal here. We're assuming no banked corners, just a flat horizontal road. That means that we know there's no total up and down force because the car is not sinking down through the road. The car is not bouncing up off the road. So the vertical forces have to cancel each other out, which means how strong is the normal force? Yeah, that's also going to be mg. And you could even get this from setting up the equations that the forces add up to 0. We know in this case, we can write out some equations. We know that the y components have to add up to what here? What do the y components of forces have to add up to in this case? Yeah, the y components have to add up to 0 because there's no vertical acceleration. There's no acceleration in the y direction. And what about the x components of forces? What would those have to add up to? Do those also have to cancel out? Yeah, those have to add up to this net force in the x direction. Because if they did add up to 0, if the horizontal forces add up to 0, that means we get no acceleration at all. But we don't want no acceleration. No acceleration would mean it continues in a straight line. We want its path to curve, so that means we have to have an acceleration, specifically acceleration towards the center. So we can say instead of the x components adding up to 0, we'd say the x components add up to centripetal force, which could also be written as mass times centripetal acceleration. And do you have any formulas for centripetal force or centripetal acceleration? How the friction and centripetal are equal? Yeah, the idea is that the x components, all the forces x components in this case have to add up to the centripetal force, which is mass times centripetal acceleration. The idea is that the y components cancel out because there's no vertical acceleration. That is, no acceleration up or down. And keep in mind, that's not north and south. Like if this map is, let's say, north, south, west, east. But this diagram is up, down, west, east. So these arrows are not north and south. These arrows are a force upwards and a force downwards. We know those cancel out because the car is not bouncing out of the track or sinking into the track. But we do need a net force to the east. There's got to be a force to the east making it curve instead of going on a straight line. And in this case, the only thing that can provide that force is friction. So the friction force is the net force because everything else cancels out. And that net force must be a centripetal force in order to be accelerating towards the center, in order to be curving in a circular path. And note that a net force towards the center doesn't mean the object is moving towards the center. It means its already existing motion is changing in a towards the center direction. Like right now, we're traveling to the north. A little bit later, we'll be traveling northeast and then east. So we're changing the direction of travel. We're not making it move towards the center. Essentially, we're just preventing it from getting further from the center by traveling in a straight line. But if we fill these in here, we can say the y components, that's just normal force plus gravity. Fn plus negative mg. So normal force plus gravity, y components. And this is ultimately why we know the normal force must be m times g, because these values have to add up to 0. The only way that can work is if the normal force is mg. So we actually know this from Newton's first law, that the sum of the forces equals 0 when there's no acceleration in that dimension. But for the x component, we can't use Newton's first law because there is acceleration. Instead, we use Newton's second law that the sum of the forces equals mass times acceleration. So that's what we'd call Newton's second law. The sum of the forces equals mass times acceleration. And you can do that as vectors, or you can do it one component at a time. Works out the same way. And in this case, we know that the sum of the forces, in this case, that's just the force of friction, because that's the only force in the x direction here, equals the centripetal force, which is mass times acceleration. And to figure out that acceleration, what aspects of the situation do you think would play a role there? What values would be relevant in how fast you have to accelerate in order to turn a curve instead of going in a straight line? Like, let's say you're in a car turning a corner. What aspects of your travel are going to make a difference in how easy or how difficult it is to turn that corner? The mass of the car, which we're already including in mass here. So mass times what other properties? Yeah, the radius is going to make a difference. Is it going to be easier to turn on a very small radius or a very large radius? Yeah, the larger the radius is, the easier the turn is, because a very large radius means it's a very gradual turn. A very small circle means it's a much sharper turn. So the larger the radius is, the less force you need. We should expect the centripetal acceleration to be inversely proportional to radius. Larger radius of circle means a smaller acceleration required. Whereas for a small circle, you're going to need a larger acceleration. Also, how would the velocity play a role? If you're traveling at a fast speed, is it going to be more difficult or more easy to stay on the curve? More difficult. The faster you're traveling, the more difficult it is to stay on the road. So we should expect the difficulty level, the acceleration required, to be proportional to velocity. If we put those together, just times velocity divided by radius, let's try that. If we just write out centripetal acceleration equals speed divided by radius, do we get the right units of measurement here? What are the usual units of measurement for speed? Meters per second. And radius is just a distance, so that's going to be meters. And we want acceleration, which is measured in what units? What are the usual units of measurement for any acceleration? Yeah, should be meters per second squared. So do these match up? If you take meters per second and divide by meters, do you get meters per second squared? No, the meters cancel out, we just get 1 over seconds. But what modification could we make to this equation? What one single change? Yeah, if we square the velocity, then that squares the units also. We get meters squared over second squared. Then one of the meters cancels out and we're left with meters per second squared. And it turns out this really is the correct formula for centripetal acceleration. And there are other ways to get to this using some more complicated calculus stuff, but I think the units of measurement approach is a very useful way to see why the values have to fit together in the way they do. We've got to get meters per second squared. One way to combine these that does that is to square the velocity. So if we write out the centripetal acceleration as v squared over r, that means the total force in the x direction has to be mv squared over r. That is the mass of the car times the speed of the car squared divided by the radius of curvature, the radius of the circle that this path is part of. So let's try that. We should be able to set the centripetal force, which in this case is just the force of friction. More generally, it's going to be the sum of all of the forces in that axis. But in this case, just the force of friction is equal to the centripetal force. Centripetal force we know is mv squared over r. And what's our usual formula for friction force? How do you typically calculate the force of friction? Yeah, mu, which is the coefficient of friction, some fraction between 0 and 1, basically describing how efficient that surface is at friction. So that's just a property of the type of surface. In this case, the coefficient of friction, mu, between tires and ground, rubber and asphalt, times the normal force. And we know the normal force in this case is mg. So we get mu times m times gravity equals m times speed squared over radius. And we should now be able to solve for speed. Assuming we know the radius, and the acceleration of gravity, and the coefficient of friction, because that's just going to be a property of the tires and the road. Also, what's going to happen to mass here if it shows up on both sides? Yeah, we can divide both sides by mass and that cancels out, which is good. You wouldn't want to have to post a bunch of signs showing different speed limits for different sizes of cars. You just want to have one speed limit that's going to work reasonably well for everybody. And then we can solve for v by doing what? How would you solve for a safe speed on this road? Yeah, multiply by r, and then, right, square root. So we're going to end up with speed equals square root of mu times g times r. Which means all you really need in order to calculate a reasonable safe speed on any curved road is multiply the radius of curvature of that road, like the radius of a hypothetical circle that curve is part of. Multiply that radius times acceleration of gravity, 9.8 meters per second squared, times the coefficient of friction between tire and asphalt. So that's a value you could look up. Take the square root of all that, and that tells you the speed in meters per second that will be just barely safe. Anything faster than that is you're going to spin out. Anything slower than that should be fine. And presumably for the actual speed limit, you want to round that down by maybe, I don't know, 5 miles per hour or something, because you know people are going to go a little faster than that anyway. So you want to underestimate the safe speed to provide safety margins. Also, how could this vary? Like, are there any such circumstances where the day-to-day conditions could change any of these values? Like, as you just go on from day to day, would you expect the radius of the road to change? No, that's going to stay the same. Once you've built a road, it tends to stay where it is. Would you expect the value of g to change? No, that's only going to be different if you rebuild the road on a different planet or something. What about the coefficient of friction? Would that change from day to day? Are there any circumstances that might alter the coefficient of friction? Yeah, if you've got, depending on the weather, maybe you've got some rain. If the road is wet, then the coefficient of friction is going to be smaller. There's going to be less friction if the road is wet and slippery. Or maybe it freezes. Maybe the road is icy. Then the coefficient of friction is going to be a lot lower. So the coefficient of friction can change. Ideally, what you'd want to do is make the calculation using a typical ordinary day coefficient of friction based on the most common weather, and set that as the usual speed limit, but also make some calculations estimating the coefficient of friction on a wet road or an icy road, and then post alternate speed limits, like saying maybe 30 miles per hour under regular conditions or 15 miles per hour under rainy conditions. So you'd want to maybe post several speed limits depending on the conditions that influence the coefficient of friction. Any questions on that so far? Oh, and someone was asking, is friction always equal to the centripetal force? Not always. It really depends on the situation. In this particular case, friction is what's providing the centripetal force because friction is the force preventing the car from spinning out. What you want to keep in mind in cases like there, well, what you want to ask yourself in cases like this is what force is making this travel in a curved path? What force in its absence would fail to make the object travel in a curved path? Like, yeah, if there's a tilt in the road, one way to make the curve even safer is to have a banked corner. Instead of having the road be flat, you have it tilted upwards. In that case, you draw out a force diagram similar to the object on a ramp. If the road is banked, and you got your car here, you still have gravity pulling straight down, but now the normal force is going to be pointing out of the road perpendicular. And we know that in this case, we probably want to split that up into parallel, or not parallel and perpendicular, but horizontal and vertical. And then also the force of friction, which could be up and to the left or down and to the right. Presumably, if you're going too fast, you're going to be skidding off this way. So friction would be pulling this way to hold you in. So you want to split that into horizontal and vertical components also. And in that case, we know the object is not accelerating up or down. So we assume all the y components add up to 0. But the x components have to add up to the net centripetal force. So in this case, you'd have just the x component of friction plus also the x component of normal force adding up to mv squared over r, the centripetal force. So in that case, both part of the friction force and part of the normal force are contributing towards the centripetal force here. And that's going to make it easier to stay on the road. That's going to mean you can travel a little bit faster still safely because the normal force is also helping to push you in towards the center. Other examples might be, for instance, let's say a planet in orbit. If you've got a planet in orbit, without any force, the planet would just travel in a straight line. So what force is making it go on a curved path instead? What force keeps the Earth traveling in a curved path instead of a straight line? Yeah, specifically gravity from what? What gravity is pulling on the Earth in a way towards the center of the orbit? Gravity from what other object? Yeah, the sun. If this is the sun and this is the Earth, gravity is pulling the Earth towards the sun. That doesn't mean the Earth falls into the sun, though, because the Earth is already in motion. Instead, the sun's gravity force acts as a centripetal force, making the Earth travel on a curved path. So the roughly circular orbit of the Earth is maintained by the force of gravity pulling towards the center of that path, in this case, the sun. Without the sun's gravity, if the sun just suddenly stopped being gravitational, if the sun just vanished, then the Earth would just travel in a straight line because there's no longer any force pulling towards the center. Any other questions on the centripetal motion stuff, or the circular motion, I mean? You're welcome. I will see you next time.